Hello everyone. Welcome to Calculus 2. Just want to take some time to talk about calculus in general, then we will spend some time reviewing some Calculus 1 concepts. And so when we think about calculus, there are two main branches, as mentioned here. There's differential calculus and integral calculus. These are some of the interpretations. Basically, when you think of differential calculus, finding derivatives, for example, the first thing you should think of is the slope of the tangent line. So, graphically, if we have a function on in the coordinate system, and that's our function, I'll call it f of x, and we're interested in the slope of the tangent line at a particular point. Well, we can't really draw the slope of a line because you need 2 points for the slope of a line, but we'll get to that concept soon enough. And let's just say that this is the tangent, cutting it just at one point. That would be the slope, and then tangent, that's our derivative, f prime of x. So we'll be reviewing those concepts, but just when you think of slope, when you think of derivative, think of the slope of the tangent. Instantaneous rate of change basically means the same thing. The rate of change of the function at that point, instantaneously. With regards to an application, velocity. If we go from point A to point B, and let's say the distance is 50 miles, and we travel that in 1 hour, then we know we're going 50 miles per hour, but it doesn't mean that that's your average rate of change, but your instantaneous rate of change, or with regards to this application, the velocity. If you could model the path of the object by a function, you'll be able to find out how fast you're going at any particular instant. And then we get to an application of, in business, marginal cost. Anytime people say the word marginal when you're talking about business calculus, that means a derivative. Okay, and then there's many other applications, although the main focus of this course may not be so much with the applications, it will be with the mechanics of differentiation and integration techniques. You have to realize that at any time there is an application. Just pick a discipline and you could find an application for it. Now, with regards to integral calculus, first thing we should think of is area under a curve. So the idea there, as you should recall, is if you have a function that, let's say, is non-negative, so let me say f of x is greater than or equal to 0 on a closed interval from a to b. So let's say this is non-negative on the closed interval from a to b, then the definite integral, recall the notation, and again we'll be reviewing this, integral from a to b of f of x, differential dx, we say with respect to x, as long as the function's not negative, that represents the area under the curve. So basically what's shaded there. So that's a classic application. Volume of a solid of revolution. If you take that and you revolve it around one of the axes, then you generate a volume. I don't know if I'm going to be able to draw this all that well, but in 3 dimensions here. That might be what the shape looks like. So that's a volume of the solid of revolution. We use a formula to calculate that. Arc length if we're going from point A to point B, we know the distance formula will get us the length of the line segment. But if we have a curved path, let's say what's in red is our path, then we could use the calculus if we could model the path of the object along the red line that I've drawn, the red curve that I've drawn, then we could use the calculus to find what we call the arc length. And then back to some applications in business, consumer surplus, that is to do with the area under a curve, or area between two curves, but there's some specifics there. And I'm using those ellipses, the dot, 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 to indicate that there's many other applications. Once again, just think of a discipline and there's an application for it. So that's the general idea for differential and integral calculus. We'll start with differential calculus, finding derivatives, and the notation. I left a lot of this blank so we could fill it in together to think it'd be more meaningful. And of course these notes are available in Blackboard. In terms of finding derivatives, that's the mechanics of differential calculus. There's a notation that we have to be used to, and if y is f of x, we could think of each of the following as representing the derivative. An easy way out is just to use the prime notation, as we know. So y prime, f prime of x. A notation that I usually use for implicit differentiation is read as dy dx. You will see me use this notation to summarize our shortcut formulas, and it's read differently. Instead of the derivative, dy dx is read as the derivative of the function y with respect to x. So this bottom notation indicates the independent variable that we're differentiating with respect to, and y is the function that we're differentiating. So we read that as the derivative of y with respect to x. Where if we use this notation, we say the derivative with respect to x of y. Okay, and that's going to be a notation that you want to get used to when we indicate our shortcut formulas. Some people will use different notation other than d dx. I like that. Since f of x is a function, of course, we could have the derivative with respect to x of f of x. Some people, you like to use the differential operator. You'll see this uppercase D with a subscript of x of y, and it means the same thing. The derivative with respect to x means the same thing as the d dx notation. And so similarly, we could say the derivative with respect to x of f of x. So be familiar with all the different notations that we use. And as you know, we have shortcut formulas that are all derived in some way from the formal definition of the derivative. And again, I wanted us to write this out. So if y is f of x, the derivative is given by, let's say, f prime of x. And you'll recall this from Calculus 1. We take the limit. I'm going to choose to use h. The limit is h tends towards 0. Of f of x plus h minus f of x, all divided by h. And this is formally provided the limit exists. Okay, so I want to show the development of this formula, although you should have seen it back in Calculus 1. I'd like to show what it means graphically so you can understand why we say the derivative is the slope of a tangent line. So graphically, if you think of a function once again in the Cartesian system, and so I'm going to call this my function just like I did earlier. And let's say we're concerned about finding the slope of the tangent line at a particular point that we call x. And once again, I really can't draw the tangent line exactly, but let's just say for the sake of argument that this is what the tangent line looks like. That's my ultimate goal, is to find out what is the slope of that tangent line. Okay, so if we label the coordinates of this point using functional notation, this would be x and f of x. So x and y, but of course y is f of x. And then if we pick a point, let's say, that's arbitrarily close to this point, we're going to leave this point fixed, and we're going to pick a point that, let's say, is h units away from that x value. And so therefore the abscissa is going to be x plus h. And then if we take the image and on the function, the coordinates of that point will be x plus h is the first coordinate, the x coordinate, and the y coordinate will just simply be the function evaluated at x plus h. So f of x plus h. And then what we do is we draw the secant line. So the secant line passes through these 2 points. So that'll be the slope of the secant. Alright, so let's calculate what is the slope of the secant. So the slope of the secant is the change in y over the change in x, or y2 minus y1 over x2 minus x1. If we label these coordinates, let's say this one is x1, y1, and this point as x2, y2, then substituting, we have y2 f of x plus h minus y1 f of x all over x2 x plus h minus x1, which is x. So the slope of our secant line becomes, well, there's nothing we can do with the numerator. That's functional notation. We don't even know what the function is. This is just in general. So we have to leave f of x plus h minus f of x because they're unique quantities. But obviously in the denominator we can cancel the x's and we get h. This is what is referred to as the difference quotient. So the difference quotient is the slope of the secant line. And now to realize the slope of the tangent line, what we could do is we could keep this point fixed, the point where we're interested in the tangent, so right here, and move the point that creates the slope of the secant line down the graph of the function until we reach that point. Now look what happens to the secant. Again, this is fixed, so the secant, there's the first secant line, there's the second secant line, there's the third secant line, and what you should be seeing basically is that secant line literally folds right into the tangent line. So what we've done is basically this. Let's say now let h approach 0, which implies, I'm going to be using these arrows to mean implies or then. If h is tending towards 0, then x plus h is tending toward x, and the slope of the tangent becomes the limit as h tends toward 0 of the slope of the secant, which is the limit as h tends toward 0 of our difference quotient f of x plus h minus f of x all over h. And you can see that that's our definition of the derivative. So that's why we interpret the slope of the derivative to mean the slope of the tangent line. Now, we're going to look at some differentiation rules from Calculus 1. And there is this document here posted in Blackboard. I suggest you print that, and these are common knowledge. You need to know these formulas. And it's posted in Blackboard under the lecture notes, and then the exam 1 folder under handouts. And so these contain all the rules of differentiation from Calculus 1 that you should be familiar with. And you can see how I've used that differential notation, that ddx notation, to indicate these shortcut formulas. This is just some standard disclaimers. K is a real number, N is a real number, F, G, U, and V are differentiable functions of X. You could use F's and G's, U's and V's, whatever you prefer. I gave both versions. And then we get down to the trigonometric functions. These are what I call the chain rule versions. So we'll be reviewing these rules now. And again, I would suggest you print this sheet, or at the very least realize that these are common knowledge. So these are formulas you should know. So definitely practice derivatives of the trig functions if you haven't memorized them already. So the first formula here, y equals 7, has to do with the derivative of a constant. And you should know that the derivative of a constant is simply 0. So we could say y prime dy dx is 0. And that's using the derivative of a constant rule. Pi is a constant, so its derivative is also 0, so dy dx, or if you're lazy, y prime. But then in question 3, we get to what I call the linear term. When we differentiate a linear term, as you can see by the formula, derivative with respect to x of k times x, remember we said k is a real number, excuse me, is just equal to k. And that makes sense because it's of the form mx, or mx plus b, and we know m is the slope, so f prime of x is just going to be the derivative of 5x, that is just going to be 5. Okay, then we get to what I call the simple power rule. And everybody knows how to do this. Just make sure it fits the differentiable form of x to the n, and then this is the result. So make sure you understand how to read this notation. It's saying the derivative with respect to x of this type of thing, something of the form x to the n, is this. And you swing down the exponent n times that same variable and decrease the power by 1. So everybody does this in a natural way. You probably don't even think about the fact that you're using this rule. To differentiate x to the 6, you just swing down the 6 times x, power 1 less than 6, 5, and we're done. Okay, there is a need to rewrite on occasion to fit a differentiable form. Notice this is not of the form x to the n. It's 1 over, or in this case t to the n, but we need to rewrite it using our negative exponent rule as t to the negative third. So the algebraic rule is that x to the negative m is equal to 1 over x to the m. So that's the algebra rule that we used here. And now we could find the derivative. You can call it y prime, but if you're going to use differential notation, this would be dy dt, because t is the independent variable that we're differentiating with respect to. And then the process, swing down the exponent, minus 3, same variable t, and a power 1 less than negative 3 is negative 4. And one agreement we need to have from the start here is that I will not accept negative exponents in the final answer. So you have to get rid of the negative exponent. We're going to use this rule once again in reverse now. The reverse of what we did the first time. Now the negative 3 stays in the numerator, and t to the negative 4th shifts to the denominator as t to the positive 4th. Okay, then we get to another example here that involves a radical. And so you have to know, most people know the square root is of x is x to the 1/2, or the cube root of x. These are the ones we most commonly encounter, is x to the 1/3. But if you see it in general, the nth root of x to the m power, it's x to the m over n. So radicals are rational exponents where the numerator of that rational or fractional exponent is the power, m, and the denominator of that rational exponent is the index of the radical, n. So in this case, we could rewrite this as x to the 4/5. And notice that it's still g of x, just like I should have pointed out here in this step when we rewrote. It was still y because we didn't do any calculus. But now we're ready for the calculus because it's fitting the differentiable form of x to the n. So now g prime of x would be, swing down to 4/5, x power 1 less than 4/5 would be negative 1/5. So make sure you're good with your fractions. And then we don't want to leave that answer again because we just agreed no negative exponents. So g prime of x becomes, okay, we already have a fraction, 4 in the numerator, and now the 5 in the denominator is joined by x to the positive 1/5. Okay, then we get to more interesting rules. The first one I wrote here, that sums and differences and constant multiples are understood, implying in number 7 that we don't have to pay attention to the formality of the sum and difference rule or the constant multiple rule. Nobody is going to differentiate these separately according to those rules. You basically just jump right in. Make sure before you start, the one thing is you have to know you could differentiate term by term, and these constant multiples of 5, negative 3, and 8 just tag along in the differentiation process. And so as long as every variable factor in each of these terms fit a differentiable form, you could just jump right in and differentiate. So f prime of x would be, swing down the 3 and just multiply it by the 5. So you get 15 x power 1 less 2. Go to the next term, that's your sum and difference rule. You can differentiate term by term. Constant multiple rule, we just used it. Constant multiples tag along in the differentiation process. So minus 3x squared, swing down the 2 times negative 3, negative 6, x power 1 less 1, no need to write it. Maybe by our special rule, the linear term, derivative of 8x is 8, and then the derivative of the constant, of course, is 0. So differentiating polynomials are very easy. Okay, now the more interesting rules. As you can see on the worksheet, or the handout that is summarizing the rules, we have products, quotients, and powers. So you need to identify them and to use the rules appropriately. And a quick example of a product rule here. I'm going to use U's and V's. I'm going to treat this as U and this as V. And so then G prime of T would be the first factor, T cubed minus 1, times the derivative of the second, derivative of T cubed, 3T squared, and the derivative of the constant 1 is 0. Then plus the second factor, T cubed plus 1, times the derivative of the first. And the derivative of T cubed, again, 3T squared, and the derivative of the constant, negative 1, is 0. So by the product rule, here's U, V prime, and this is plus V and U prime. If you do it in the opposite order, I usually just say first derivative of the second plus second derivative of the first. If you do it in the opposite order, that's fine. You'll get the same answer. It'll just look a little bit different along the way. But then you want to clean things up. So G prime of T, just do the obvious algebra. Distribute this 3T squared, get 3T to the fifth, minus 3T squared, then plus distribute this 3T squared as well, get 3T to the fifth, plus 3T squared, and now combining like terms, we get 6T to the fifth, and looks like the T cubes, or excuse me, the T squareds cancel each other out. Okay, next example. Obviously a quotient. Treat it as U over V. And perform the quotient rule. I'm going to say dy dx. You could say y prime if you like. It is a fraction. And we start with the denominator. 2 minus 7x. Derivative of the numerator. 3. Minus numerator is a binomial quantity, 3x minus 5, times the derivative of the denominator. Be careful here, that's negative 7. And that's all over that denominator, 2 minus 7x as a quantity squared. So with regards to the quotient rule, there's VU prime minus UV prime all over V squared. And if you have different memory devices to remember that, that's fine. I always use U's and V's. But honestly, when I think of it in my mind, I always just say denominator derivative of numerator minus numerator derivative of denominator all over the denominator squared. And then as always, clean up your algebra. We'll distribute this 3, do the natural algebra. We get 6 minus 21x. Okay, here, as you think of distributing this negative 7, also think of distributing this negative. So really what you're distributing is a positive 7. So times 3x is plus 21x, and times negative 5 is minus 35. And that's all over. You want to leave this binomial squared in the denominator. Excuse me. No need to expand that. Okay, and then combining like terms in the numerator, dy dx would be, looks like the 21x's are gone. 6 minus 35 is minus 29. And again, leave this 2 minus 7x that's being squared. Okay, and then here is what we could refer to as the general power rule. Some people will call it the chain rule, but I want to talk about the chain rule more specifically. This is better referred to as the general power rule, as you'll realize once I formally talk about the chain rule with you. If you want to go back, you can make sure you say this is a product This was quotient. And this is going to be general power. If you want to call it chain, it's not wrong, but that subtle detail will come out through discussion momentarily. But it's fitting the form of u to the n, where you have some function of x raised to a power. And so, as you can see on the formula sheet, the derivative with respect to x of u to the n is similar to differentiating x to the n, where we swing down the n, same quantity, power 1 less, but then it's a consequence of the chain rule that we take the derivative of what's inside. And so we'll show that formally through the chain rule, but to use this rule as it is, which is the best way to proceed, we're just simply going to, I'll call this dy dx. We're going to swing down the exponent of 7, then that same function, x to the 5th plus 1, unchanged to the power 1 less than 7, which is 6, and then the derivative of the inside. And term by term, the derivative of x to the 5th is 5x to the 4th, and the derivative of the constant is 0. And so with regards to the formula, there's our nu to the n minus 1, and that 5x to the 4th represents the all-important du dx. And to simplify this, the only thing we could do, can't go inside the binomial here because of the power. We could take the 5x to the 4th, multiply it by the 7, so we get 35x to the 4th, and then that quantity, x to the 5th plus 1 to the 6th. Okay, so I'm going to stop this lesson here. This will be part 1 of our calculus review, and we'll come back and do the rest of it in a second part.